Hello students, my name is Shashank Shekhar. So we started the chapter Electrochemistry yesterday and we have seen the various type of cells. And then in the second lecture, we have seen that what is galvanic cell specifically and how does it works and what are the various components and what are their uses in this galvanic cell. So today will be the third lecture of this electrochemistry chapter. So this is our syllabus that we have. So if I see the syllabus minutely, so we have covered this part in the first lecture, then this part in the second lecture. Today we will be starting from here, right? So we'll be doing these things. We will be starting from the standard electrode potential and Nernst equation and its application to chemical cell. So this will be our today's topic. Now, if you look at the detailed topics of this today's lecture, it will be standard electrode potential first of all. Then we will see what is standard hydrogen electrode or SHE. After that, we will see that how we can use that SHE or standard hydrogen electrode for measurement of this standard electrode potential. Okay. Then we will move to Nernst equation. So basically, this is the most important lecture of whole of this electrochemistry because questions are often asked from this Nernst equation only. So you will be asked to calculate the EMFs and all. So this is the most important topic for today's class and you can say for the whole electrochemistry chapter. Then we will see how can we apply this Nernst equation and find out the E cell using an illustration in which I am using the Daniel cell as our illustration subject. After that, we will arrive at a general form of Nernst equation which can be used in any cell, and then we can see that how this general form is applied upon various type of cells. So let us start our today's class. So before moving to our today's topic, I will first tell you something about yesterday's cell representation. So this is important for this lecture also. So I'm just giving an overview again. So if you see at the cell reaction that is given here, so you can see that we have copper and it is going to Cu2 plus. So how it will go to Cu2 plus? By losing 2 electrons. Then only it will have a charge of +2. So it will lose 2 electrons, -2 electrons I'm writing here. Similarly, here 2 silver atoms, I am taking 2 silver atoms to maintain the charge neutrality. So 2 silver atoms, or you can say specifically 2 silver ions, are losing 2 electrons to go to 2 Ag metal. So this is our second part. So first one, the Cu is losing 2 electrons and Ag is gaining 2 electrons. So since copper is losing 2 electrons, it will be the oxidation part, and silver is gaining 2 electrons, so it will be the reduction part. So if I want to represent this cell, we can represent it as Cu, which is going to Cu2 plus, and Ag plus, which is going to Ag. Now one more bar will be here. Why? 2 bars are usually present. 1 bar can also be present depending upon the cell assembling. So if there is a salt bridge, then we will represent that we will have 2 bars. So basically 2 bars represent that we are taking 2 compartments, and if we have to take 2 compartments, then we need to have our salt bridge. But suppose both of the electrodes are submerged in the same compartment, then in that case we will have only 1 bar. Now I have told you earlier, what is this 1 bar representing? This 1 bar is representing that this is in solid phase and this is in aqueous phase. So it is a kind of phase boundary we are giving between solid and aqueous. Similarly, this is the phase boundary between aqueous silver ion and solid silver. In between we have this 2 bars which is representing that with both these compartments are kept apart or they are not mixed with each other, right? Now one more important thing to notice here is that we are moving from here to here. Always keep this in mind that the convention that we are following is that we are moving from left to right. So copper is going to copper 2 plus and Ag plus is going to Ag. So this is our convention, right? Now if you are asked that, okay, calculate your E cell. So I have told you earlier that in case if it is given that both of the reduction potential are given, then in that case what we will do, we will convert one of the reduction potential to oxidation potential. So basically I mean here that, so I mentioned in the earlier class also, that while we are finding out the EMF, we sum the reduction potential of the species getting reduced and the oxidation potential of species getting oxidized. That is the rule you have to follow. Here you can see that we are subtracting right and left. Why we are doing so? Because we are given with the electrode potential of Cu2 plus going to Cu. But in this case, you can see that Cu is going to Cu2 plus. So this is the reduction potential, you can say. Reduction potential. Okay. And we can see that Cu is not oxidized. So we can see that Cu is not reduced here, but it is oxidized. Why? Because it is gaining 2 electrons. Okay. So we have to remember that we have to now reverse the sign of it. Because it is not getting reduced, it is getting oxidized. So what we will do, we will just reverse the sign. So if it is ECU2 plus ECU, we are taking a negative of it. And then we are adding both of this to get our E cell. Now one more thing is to notice here is that if you look here, this E representation, the EMF representation, you have to keep this in mind also. So it is also following the same convention, going from left to right. So if this is the case, this is given, then it is the electrode potential that is required from going from Ag plus to Ag. Similarly, this is from Cu2 plus to Cu. Now, if it is written in this way, suppose Cu, then Cu2 plus, then we will say that it is given for Cu going to Cu2 plus. Mean it will be the oxidation potential in that case. Oxidation potential. But here it is given that Cu2 plus is going to Cu. So it is the reduction potential. Reduction potential. So you have to keep this in mind, the cell representation and plus the EMF representation. So both are important in the further slides that I'm going to discuss right now. So this was from the yesterday's class that you need to remember for today's class. So let us start our today's class. So the first one is standard electrode potential. So we will be knowing what is this standard electrode potential. So in standard case, what do? We take the half cell concentration that is involved in our electrochemical cell as unity. So the concentration of all the species involved in half cell is taken as unity. So in that case, whatever will be the electrode potential will be considered as standard electrode potential. Again, what is standard electrode potential? Standard electrode potential is that potential which is the potential when the concentration of all the species involved in half cell is unity. So we call it as standard electrode potential. So the key points are, the first one is the concentration of the salt in the left compartment is taken as 0. Also, the concentration of the salt in right compartment is taken as 0. Then in that case, the EMF that we will get of each of this, or the EMF that we will take for each of this electrode, will be our standard electrode potential. So how do we calculate the standard electrode potential? What do we do? So we have taken hydrogen as our reference point. So let me make it more clear. So we take hydrogen in one compartment. How do we take hydrogen? That is a different case. We'll be seeing that in the next slides. But for now, consider that we are taking hydrogen in one compartment, and the metal whose electrode potential is to be considered, we are taking in other compartment, and then we are calculating the EMF, and whatever may be the EMF is considered as our electrode potential of that given metal. And if the concentration is taken as 1, then it is considered as our standard electrode potential of that given metal. So this is our thing. Now, two things are to be noticed here. First is, if you are getting a negative E0 value, what we are getting a negative E0 value, means the redox couple is a stronger reducing agent than H plus or H2. So if you are getting a negative electrode potential, then we will consider that it is a stronger reducing agent. How we are considering this? So first of all, we are taking the standard EMF of H plus as 0. H plus or H2 as 0, right? So we are considering it at 0. So if we are getting it as negative, means the reduction potential we are getting, it is negative. It means that it is a better reducing agent, means it will get oxidized easily. So in that case, we will say that it is a stronger reducing agent. But if we get a positive value, it means that it can be reduced easily. It can be reduced easily, but it is a weak reducing agent and hence a strong oxidizing agent. So these are the 2 points you should remember about, say, hydrogen electrode. In comparison with hydrogen electrode, if you are getting a negative value of E0, means that it is a strong reducing agent than your H plus and H2 couple. And if we are getting a positive, it means it is a weaker reducing agent than H plus and H2 couple. So this is our standard electrode potential. And I have told you that we are taking hydrogen in one side, and on the other side we are taking the metal whose electrode potential we want to consider. But how do we take this hydrogen? That we'll see in next slide. So we kind of take a standard hydrogen electrode. So we'll see in more detail what is the standard hydrogen electrode. So this is our standard hydrogen electrode that we should take. So if you look at the structure of this standard hydrogen electrode, it consists of platinum electrode. So this is our platinum electrode. Okay, this is our platinum electrode, right? Now this electrode is dipped in acidic solution and pure hydrogen gas is bubbled through it. Since we cannot take this hydrogen in aqueous form, it is not possible to do so. So we supply it in the form of gas, and the metal electrode that we will take will be our platinum. So this should be remembered. Now, why we are taking acidic solution? Basically, we need the salt of that same hydrogen gas. So we are taking HCl, and HCl will make a acidic solution, of course. So one more thing, the concentration is taken as 1 molar because we are calculating standard, and I have told you that the concentration should be unity of the salt whose standard hydrogen electrode we are considering, or standard electrode potential we are calculating. Therefore, we are taking the concentration of H plus here as unity or 1. One more thing. Now, since we are considering gas, so we cannot consider it as the concentration term. So we do take it as the pressure term for our electrode. So what we have done, we have taken 1 atm pressure, or we have maintained 1 atm pressure in this electrode. So I mean here that the hydrogen gas we have taken is kept at a pressure of 1 electrode, and the concentration in the salt is also taken as 1 molarity. So then only we can consider it as standard hydrogen electrode. So these are our complexities that you should remember. So the first is that we are taking platinum rod here, or the platinum electrode here, and finally divided platinum foil as the main component that can be exchanging our hydrogen gas. Then in the next, we have taken hydrogen gas in the electrode in at 1 bar pressure, and we are bubbling this through the water. So what is this bubbling you mean? So you must have seen that if we take a mug that is vacant and keep it on the surface of water, then we will face difficulty in pushing it down because of the air that is present. Now if you just lift the mug from one side by slighter mean, do it like this, so you will see that bubbles will come out. Why is it so? Because the air that was present in the mug will try to escape and form bubbles, and will escape through bubble form out of the water. So if we are supplying here gas, so we are supplying here gas, now gas will be present here. Now if it will try to move further and come out of this electrode, it have to make bubbles and then move out of it. So basically we are taking an aqueous solution of this hydrogen, which is HCl, and we are supplying the H2 also, which is the gas, and both of these have different oxidation state. So we'll see it later what is the cell representation and all, what are the equation involved. But for now, consider that we are considering hydrogen and we are bubbling it. Bubbling it means we are pushing air through this electrode and it is coming out of water in the form of bubbles, of course. So these are our complexities that we have to take a note on about standard hydrogen electrode. Now we'll see how can we use it to calculate the electrode potential of different metals or different you can say different elements. So whatever will be the required element, we will use it this standard hydrogen electrode and calculate their electrode potential. Or you can say if you are taking SHE, then we will calculate standard electrode potential. So let us see this. So here is our arrangement that we are taking. Okay, so this is our arrangement. Now several things are to be noticed here. So at 298 Kelvin of the cell, standard hydrogen electrode second half constructed by taking standard hydrogen electrode as anode and the other half as cathode gives the reduction potential of the other half cell. Now what is written here is that we have taken hydrogen at the left side. So this is the hydrogen compartment. You can see it very clear. We have taken our platinum. We are bubbling hydrogen gas at 1 atm pressure through it. So it is kept at oxidation side. Now whose electrode potential is to be calculated is kept on the right side. This is on the right side, and suppose we are calculating it for zinc. So we are keeping zinc here. Now pure zinc is taken here. Again we have introduced our salt bridge to maintain the electron neutrality, and this is our complete circuit. Now if you consider what are the concentration and all, you can see that we have maintained a temperature of 25 degrees Celsius. It is our standard temperature. So we'll calculate the standard electrode potential at a standard temperature only. Now since we have taken SHE, hence we are calculating standard electrode potential. Therefore the atmospheric pressure of the hydrogen gas that is to be bubbled through it is taken as 1 atmosphere, and the concentration of H plus ion is also taken as 1 mole per decimeter cube or 1 molar. If we consider the right side, that is the zinc side, so we can see that we are taking zinc salt, and here also the zinc salt is taken in the standard form, that is 1 molar concentration. So I have mentioned it earlier also, I am mentioning it right now also, that for calculating standard electrode potential or the standard electrode potential is that potential at which the concentration of the salt in the compartment is taken as 1 molar. So here we are taking it at a 1 molar. So the whatever will be our standard electrode potential will be our potential for this metal. And how it is so? Because we have considered the hydrogen as 0. So whatever we get our EMF will be only due to this zinc electrode. So you can just imagine it in your mind. So if we take something as reference, means we are taking that thing as 0. and whatever we are calculating will be our value for that metal or that species or that couple, whatever we are taking, or that redox couple, right? So we are taking a hydrogen as 0, and whatever EMF we will get through this, say, voltmeter, will be the standard electrode potential of the metal that we're taking on the right side. So is it clear? Okay. Now you should also remember what are the standard condition. We are taking 25 degrees Celsius. We are taking 1 atmospheric hydrogen. We are taking 1 molar concentration of this H plus ion, and plus we are taking 1 molar concentration of this zinc salt. All are this setup that we're taking. Now, if the concentration of the oxidized and reduced form of the species in the right hand half cell are unity, then the cell potential is equals to the electrode potential of the given half cell. So the same thing is written here also, that we are taking the unity concentration of on both the compartments, and hence whatever will be our electrode potential or EMF will be our standard electrode potential for the given metal. So in this case, if suppose we get an EMF of, say, this cell as X volt. Suppose we got this as X volt. Okay. Now what we will do, we know that E of the substance which is getting reduced and E of the substance which is getting oxidized is equals to the EMF of the cell. Okay. Now how we will identify that which one is getting oxidized and which one is getting reduced? So it is done experimentally basically. So if you see that zinc metal is depleting, so we have taken it as left side because we have to consider with reference to this. So we are just calculating reduction potential. So if you want to know the reduction potential, you have to keep it on the reduction side. But it is not, it is just a convention. It will not always happen that hydrogen will be getting oxidized and zinc will be getting reduced. The opposite can also happen, that zinc can get oxidized and hydrogen can get reduced. So how will get it that if it is getting oxidized or if it is getting reduced? So if you just simply see the metal, and if the metal is depleting, means the metal is getting oxidized because it is going into the solution. So if the metal is depleting, then it is getting oxidized, then whatever will be the EMF will be our oxidation potential. Okay. And we know that this hydrogen is getting reduced, so it will be 0 plus E oxidation and E. So this is our oxidation potential. Now if we are interested in reduction potential, so we will just take the negative of it. Similarly, if you are, say, calculating and you got that this metal is getting bigger and bigger, or the metal that is deposited on it getting increased with time to time, then you will say that it is getting reduced. Then in that case, we will directly get our reduction potential. So whenever we will see question, we will get a more clear idea of this, what is the application of our, say, this thing EMF and all. For right now, you can consider that using this setup we can calculate the standard electrode potential. Now we'll move to the most important part, that is our Nernst equation. Now I will just give a general formula for it. In book you must have seen that it is written that oxidation by reduction, ln oxidation by reduction, or something like that. The problem with that equation is that sometimes that equation does not fit or does not go easy to be put forward along with the cell representation you are given. For that case, you should remember the general form. I have done the same for this EMF cell also. So in books you will often see that we are just subtracting E reduction of the given by minus E reduction of the species getting oxidized. Basically I am saying that in book you will see that if you have to calculate the EMF, it is written as EMF is equals to reduction potential of the species getting reduced minus the reduction potential of the species getting oxidized. But it is not so. In you can say, if you want to imagine it physically, then the more general formula would be the reduction potential of the substance getting reduced plus the oxidation potential of the substance getting oxidized, and the sum will be our oxidation potential, sorry, the EMF of the cell. Okay, then will be our EMF of the cell. Now here also I am using a general approach. I am saying that okay, we are going from here to here, A to B. Okay, then we will write that the EMF of the cell can be written as E of A going to B is equals to E naught of A going to B, that is the standard electrode potential for A going to B, minus RT by NF ln Q. So this is our general formula. You can apply it anywhere you want. And we will also see that how we can apply it on the Daniell cell and all of the coming electrodes. Now the thing here to notice is that what are this N, F and all. So if you consider N, that it is the number of electron involved. It is just the number of electron involved. You do not need to be worrying about what is happening. It is getting the losing of electron, it is having gain of electron. You just have to see that how many electrons are involved. Suppose from going from A to B, 2 electrons are involved. Suppose A is taking 2 electrons and going to B. Then in that case, N will have a value of 2. But if the opposite is happening, A is going to B by losing 2 electrons. That do not get confused that it is losing 2 electrons, that it can be negative and will be minus 2 or something like that. You will just consider the same value of 2 again. You will just say that it will be also 2. Okay, is this clear? Now next is Faraday constant. What is this Faraday constant? So its value is 96500 coulomb. What is this 96500 coulomb? So for those who don't know, it is the, you can say, the charge due to 1 electron, 1 mole of electron specifically. What it is? It is the charge due to 1 mole of electron. So if you multiply this, if you know what is 1 mole, it is 6.022 into 10 to the power 23. And we know that the charge on 1 electron is 1.6 into 10 to the power minus 19. So 1 electron holds a charge of this much. So 1 mole will hold the multiplication of this one, and you will get it as this thing. So by definition, 1 Faraday, you will see this in the Faraday law of electrolysis also. What is 1 Faraday? But I'm just giving a glimpse of it as we have used this term. So it is basically the charge which is due to our, say, 1 mole of electron, that is due to 6.022 into 10 to the power 23 electrons. The charge on that much amount of electron will be our Faraday constant, and its value is 96500 coulomb. So you can say it coulomb per mole more accurately, coulomb per mole, because it is the charge that is beared by 1 mole of electron. Now what is this EAB? It is simply the electrode potential of A going to B. So whatever will be the electrode potential for A going to B will be our electrode potential of EAB. Now if we are considering this EAB as our EMF, then we have to use the standard electrode potential for A going to B to calculate it. So this is the thing we are calculating. So basically we know that what are the concentration of A and B. So we can put it in Q, and we know that what is the standard value. These two things we often know, and we have to calculate this one. So we just keep all these values here and here, and then we get our standard electrode potential. Using standard electrode potential, we get our electrode potential of our given cell. At last we have this Q, which is the reaction quotient. Now this reaction quotient can be pressure reaction constant also, or concentration reaction constant also. So we can see, we will see it later in the next slide. So this is our Nernst equation. So this is the most raw form of this Nernst equation. Now I will just simplify it further to get it more handy in your given questions. So this is our modified form. Let us illustrate this or get the modified form using our Daniell cell illustration. So this is our Daniell cell equation, if you remember, in which zinc is getting oxidized and copper is getting reduced. Zinc is getting oxidized and copper is getting reduced. So if we consider first of all the reduction potential or the reduction half cell, basically we will consider the reduction half cell. So if you write the reduction half cell reaction, it will be written in this way. So you should know this, how it is written. So if you consider this reduction, so this is species getting reduced here, it is gaining 2 electrons. So I'm writing this as Cu2 plus 2 electron going to Cu. We can write it, no problem. Very balanced equation. Cu is 2 plus is going to Cu by gaining 2 electrons. Now I have told you earlier that for A going to B, it was EAB is equals to EA not B minus RT by NF ln Q. So we will write that same thing here. So we are going from ECU2 plus 2Cu. So I have written this, and we have taken the standard reduction potential for the same species minus RT by 2F. Why I have taken 2 here? Because the number of electron that is involved, it is 2. So the value of N will be equals to 2. Right? Now ln Q. So I have taken Q is equals to 1 by Cu2 plus aqueous. So do not get confused with it. It is very easy to understand. We know that Q is equals to, which is reaction quotient, is equals to the product's concentration, which is Cu solid, by reactant concentration. So this will be our say our thing. But you will say, sir, you have not taken this Cu solid. So students, you must know that if you are taking a metal Cu solid only, then its concentration will be 1 unity, because only that thing is present. So what is the significance of saying concentration here? It is just that metal only present in the electrode. So we will take it as 1. So this Cu solid is taken as 1. So if you want to do, just imagine it in your mind. So what is the formula of molarity? It is number of mole present in one volume or one unit volume of that solution. What is the number of moles that is present? Suppose X number of moles are present. And in that we have only that solution. So it is not a solution also. It is just a metal. So its concentration will be 1. So we can say that, I can just glorify a little more and say that the concentration of pure elemental form will be always unity. A more general statement I like to make is that the concentration of all pure element will be always unity, because the concentration term has no significance if we are taking pure thing. Concentration term arises when we are taking solution. In that case only we are taking this concentration term. So therefore the concentration of CuS is taken as 1 or unity, and we are left with this Cu2 plus aqueous. So the overall equation will be ECU2 plus going to EU, means electrode potential due to Cu2 plus going to Cu, is equals to the standard electrode potential of Cu2 plus going to Cu minus RT by 2F, where 2 is the number of electrons involved, ln 1 by concentration of copper 2 plus ions or copper 2 plus aqueous ions. Right? Similarly, we can write the same thing for oxidation potential. How we can write it? So this is our thing. So if you write the half reaction or the oxidation half reaction, it will be written as Zn going to Zn2 plus. Yes. Then how it will go to Zn2 plus? By losing 2 electron. And the Nernst equation can be written as, since we are going from Zn to Zn2 plus, so it will be written as E of Zn going to Zn2 plus is equals to E naught of Zn going to Zn2 plus. It is basically our standard oxidation potential. standard oxidation potential. Why it is taken as standard oxidation potential? Because we are getting zinc oxidized. So suppose you are given with standard reduction potential rather than standard oxidation potential, then what you will do? You will simply take the negative of it and put it here, right? Then further we have minus RT by 2F. So again 2 electrons are involved, Ln. Now if you see here, on the product side we have now our Zn2 plus or our zinc ion in the aqueous form. Therefore we will write it on the top, because Q is equals to product by reactant, and we know the concentration of reactant is taken as 1 because it is pure metal. Therefore these are our two equations. Now if you remember from the previous discussion, I have told you that if you are writing the EMF of the cell, then what it is simply the addition of the electrode potential, or you can say the reduction potential of the species getting reduced plus the oxidation potential of the species getting oxidized. So which is the species that is getting reduced? It is copper. So we will add this plus this, and this will give our, means I am saying that ECU 2 plus Cu plus Zn2 plus is equals to, so if you add both of this, you will get your E cell. Upon adding this, we will add this 2 also, this and this will be added, and this will be equals to our E0 cell. So E0 cell is basically E0 Cu2 plus Cu plus E0 Zn2 plus. This will be our E0 cell minus RT by 2F. Again we have taken RT by 2F common, and we have used a simple logarithmic property which says that ln A plus ln B is equals to ln A plus B. Sorry, ln A into B. ln A into B. So we have multiplied these two things, 1 by Cu2 plus aqueous multiplied by Zn2 plus aqueous by 1. So you will get this one. Ln will be on the outside because it is ln A plus ln B is equals to ln A into B. We have taken negative sign common also. Now let me erase all this. So this is the most important formula that we get. Now if you want to generalize this one again, then we can generalize this too. So this is our general form now. So I am saying that if we are having a general electrochemical reaction like this, in which AA plus BB is going to CC plus DD, and N electrons are involved in this, then we will write it E cell is equals to E0 cell minus RT by NF ln Q, where E0 cell is the standard EMF due to reaction of this A and B, minus RT by NF ln Q. Now this Q is again reaction quotient, and it will be equals to different terminologies depending on what we are taking. If we are taking only liquids, say we are taking only liquids, then in that case it will be concentration. So the concentration of C multiplied by concentration of T, and since we are taking Q, so we will take their C and D. So since we are considering Q is equals to QC, we will write it as E cell equal to E0 cell minus RT by NF. Then we know what is Q. If you remember from your 11th class theory, we can write reaction quotient as concentration of C raised to the power coefficient of that C multiplied by D, then raised to the power coefficient of that D, A raised to the power coefficient of A, and B raised to the power coefficient of B. Now if you write it for pressure, in the terms of pressure, suppose all of the species that are involved are gases, then what we will do? We will say that E cell is equals to E0 cell minus RT by NF ln pressure of D multiplied by pressure of C divided by pressure of A multiplied by pressure of B. So this will be our equation in case of gaseous species. Okay, so we have written this thing. Now we are left with how we can apply this Nernst equation. So in the exam we are given often this cell representation. That's it. And we are asked that now you calculate this E cell. So how we'll do it? So I have explained it how to explain the cell notation. So you have to write this very neatly, first of all, the equations and all, before moving from this to this. So if you are writing for this, how will you write it? So we are going from H2 to H plus here. This is clear from this equation. I have told you we'll go from left to right. Now let us balance this equation first of all. So we are going from H2 to H plus. But here two hydrogen atoms are present, here only one is present. So we multiply it by 2. Now H2 will take how many electrons to go here? It will take plus 2 electrons. So 2 electrons will be given out. Similarly, we can write this as this thing. Now you are asked that write the EMF of this, or the standard half EMF of this using Nernst equation. So how you will write it? So E of these species is equals to E naught minus 0.0591. So I will tell you what is the 0.0591 later on. Suppose this is right now for RT by NF. I will tell you how it is 0.0591 later on. Log concentration of these thing. Yes, concentration of this, which is H plus. And what is the power of this? So it will have a power of 2 here. Sorry for the mistake. So since it has a coefficient of 2, so it will have a power of 2. And hydrogen gas is present in, suppose the pressure here is pH2. Therefore we will write it as pH2. It is having no power because no stoichiometric coefficient is present here. Further, if you want to write this equation, simplify it further, you can write it as E naught is equals to E is equals to E naught minus 0.0591 by N will be 2 here, log H plus square by pressure of H2. So this will be our final equation, right? So this will be our final equation. Now I will ask that what is this 0.0591? So it is basically the value of RT by F at standard condition. What are the standard condition? The temperature is taken as 298. Okay, R is, you know the value, 8.314, F 96500. So if you evaluate putting all these values, you will get it as 0.0591. Next we have another example. Here we have a complete cell. So this was a half cell. Now this is a complete cell. So you have to write both the equations. So we are going from Ni to Ni2 plus. That is losing 2 electrons. And we are going from Ag plus to Ag. So it will gain 1 electron. Now listen here, an important point. While we are adding such two equations, you have always to be balance this equation. Means it is always required to balance this equation by balancing out the electrons. You can see here we are having 2 electrons, but here we are having only 1 electron. So you have to balance this so that overall we have left with no electrons in our final equation. So we multiply it by 2 and then we will add it. So we'll get it as Ni 2Ag plus. This will get cancelled out, this and this, and you will get it as Ni 2 plus and 2Ag. So if you write the Nernst equation for it, it will be E cell is equals to E naught cell minus RT. Now how many electrons are involved? 2 electrons. You will take the maximum one, not the minimum one. We will take the maximum one. Or you can say after balancing out, whichever gets cancelled, means which electron is getting cancelled. Here 2 electrons and 2 electrons are getting cancelled. So after balancing the equation and balancing the electrons in both equations, whatever will maybe the electrons involved will be our n here. So in this you can see we are having 2. So 2 will be written here ln. In the final equation you can see that we have Ni2 plus on the right side, on the product side. So it is written on the upside, Q is equals to product by reactant, and we have Ag on the left side with a coefficient of 2. So we have raised it to the power of 2. And therefore you get our final equation, Nernst equation for the given cell representation. So you should remember all this step one by one to finally find out our Nernst equation. So it is very important to apply or to use the cell representation to write our final Nernst equation. Now the thing to notice here is that we have introduced the pressure term. So if there is a case that we have both gases and liquids involved, right? If you have both gaseous and liquid state involved, then in that case we will use both the concentration and the pressure term to write our Q, final Q. As here we have HCl and plus we have this gaseous hydrogen. So we have taken H plus ions divided by pressure of that H2. So this is our final equation for the given equation or the given cell notation. So this was for today's class. So we have basically seen what is Nernst equation and how can we apply this Nernst equation to different types of cell. So thank you for today's time. With this, I end my lecture.